Hello, welcome to the 11th video of this course. So, we were in the last video, camera got switched off and we were almost here. So, we wanted to prove that any convergent power series is real analytic in its domain of convergence. So, domain of convergence is the disk with center at the point around which the first series expansion is done, and with radius as the radius of convergence. All right. So now what we need to show by this is, if we are given a power series which converges here, so we can assume R to be the radius of convergence. What we need to show that around every point in this neighborhood, you will have a small r greater than 0, such that and a power series around B such that both the power series are equal on the intersection. Alright? Yeah. So we'll use this exercise for proving this. Alright, so we started the proof. We wanted to show like that. Now what we want to do is look at the power series summation. So proof continues. Summation n equal to 0 to infinity n x minus x minus x naught for n. Now each of the term we will do something like n equal to 0 to infinity n x minus b plus b minus x naught to the power n. Right? Now this is we'll expand this as binomial expansion, and we want to change the order of summation here. Alright? Once we can do that, then we will be done. Now the point is, we want to show the series converges. So we need to find an R. So let me draw a picture, which I have drawn last time also. So here was something like that. So we had the point x naught, and this is x naught minus r, and this is x naught plus r, and b is somewhere here. Alright. So what you want to choose is choose R as capital R minus mod of B minus X naught. Alright. Or we can make actually any R less than this number. So not necessarily equal, but take R to be equal at this point. Alright, so now expand it. Now from here you expand n equal to 0 to infinity an am equal to 0 to n nc0 ncm x minus b for n b minus x naught for n minus n. Alright. What we need is to interchange this summation. So we want to show this converges. So look at this one. Summation n equal to 0 to infinity, and all this term is is Bn here. So mod An summation n equal to 0 to infinity NCn mod of x minus b for m mod of b minus x naught for n minus n. Alright. Now look at this series, this one, which is less or equal to summation n equal to 0 to infinity mod an mod of x plus b x minus b plus b minus x naught for n. So this total number from here is r, right? So this is less than r. This number, this sum is less than capital R. Alright. So when this x minus b is less than r, then the sum is total. So you take r to be strictly less than this. So here it is, x minus b less than r implies x minus b plus b minus x naught, which is r, which is less than r plus b minus x naught, which is yeah. I'm sorry, this equality also work, no problem. Yeah, getting confused sometime. So this is equal to r. So you see, when x minus b less than r, then this one is less than capital R. So this is less than capital R. So hence this converges. Alright, so this converges. Yeah, this converges. Hence, we can interchange. Like this, we can interchange the limits. So we can now interchange the two summations here. So from 1 interchanging the sum, the order of summation which approved by the exercise we get the following, which is summation m from 0 to infinity, summation n from 0 to infinity, an b minus x naught power n minus m and x minus b power n. So this is the coefficient. So this is summation m equal to 0 to infinity bm x minus b power m, where bm is summation n equal to 0 to infinity and b minus h naught or n minus n. There is some LCM missing. LCM. Yeah. Right. So this is what it is. So you have equal. We get the direct equality here. This is true. All these things true for all x minus b less than r. Alright, this proves this one. This proves this. Any convergent power series is real analytic on its domain of convergence. Alright. Now this gives a lot of example of real analytic function. And the proof of complex analytic case is similar. So I'll put it as exercise. Follow the same computation. You get it. So I put as an exercise. So maybe I should put theorem. Convergent power series is real analytic on its domain of convergence. Then a convergent power series convergent power series. So in this case, we proved the domain of convergence was an interval. This was an interval. For power series in real variable. So similarly, a convergent power series in Z is complex analytic. On its domain of convergence. So in this case, it is a disk. Alright, so proof is exercise. Follow all the steps in the previous proof. Alright. Now what this two theorem gives us is our examples. So we defined it on an example. Maybe I should erase first. So example, so e power x summation x power n by factorial n from 0 to infinity is real analytic on R, and similarly e power z, which is summation n from 0 to infinity z to the power n by factorial n is complex analytic on C. So example 1 is 2 summation z to the power n from 0 to infinity is complex analytic on the image disk. Similarly, summation z to the power n by n is also complex analytic on disk. Alright. Alright. So next what we want to look at is so the convergence note. The convergence for power series we have taken assumed or defined is absolute convergence. Pointwise. But you know, a sequence of functions converges absolutely, but converges pointwise, the limit function may not even be continuous, right? So is a power series, once it converges, is it continuous at all? Alright? So we know power series is real analytic, but real analytic is defined in terms of power series only. The question, it's very simple question, is a real analytic function, or maybe convergent power series. Does a convergent power series perform a continuous function on its domain of convergence? So the question is whether the power series, which is convergent pointwise absolutely, does it give a continuous function? These are valid questions. If we want to study differentiability, the first thing is this one. So the notion, we need to find a right notion to, of course this is a right notion, but whether somehow or the other uniform convergence is coming from there or not, we need to see. Once we can, if we know that the path series converges uniformly on certain sets, then you can provide continuity. Alright? So let me recall the definition of continued uniform convergence. Suppose Fn is a sequence of functions on a compact A subset of C. We will look at subset of C only, but it's true in general metric space. Fn is said to be to converge to F uniformly if for every epsilon greater than 0 there exists not n such that mod of Fn minus F less than epsilon for all n bigger than n naught. Alright. So the important point is that uniform limit of continuous functions is continuous. If we show that a path series converges on every compact subset of its domain of convergence, then we get continuity for free. Alright? So this is the we'll show that that path series converges uniformly on every compact subset of its domain of convergence. Alright, and then there are a few more questions which we'll state in the beginning of next video, which is about differentiability. Once continuity is settled, whatever differentiability, right?